Welcome to a deep dive into the AutoByteus software engineering team. In this detailed walkthrough, we will explore the powerful agent configuration, the strict skill definitions, and the comprehensive templates that allow these agents to perform end-to-end software engineering.
This is a highly sophisticated team of specialized agents working together under strict rules to deliver complete end-to-end software updates. We'll start by looking at the solution designer. This agent acts as the architectural spearhead for the entire team. Its mandate is to bootstrap the task context, investigate the codebase deeply, refine the requirements, and produce a comprehensive design specification before any implementation begins. Every agent's behavior is driven by its skill file, a detailed markdown document that acts as an operating manual. For the solution designer, the skill defines its core purpose, investigating requests deeply enough to produce a design-ready requirements basis. It outlines exactly what the agent owns, from the bootstrap context and problem framing to deep architecture investigation, root cause classification, and the final production of the design spec and investigation notes. It ensures the agent doesn't just write code blindly, but instead understands boundary ownership, legacy constraints, and data flow spines before making decisions. The skill file contains rigorous, non-negotiable rules. In the Bootstrap and Environment Discovery section, the agent is instructed to resolve its workspace root, identify the repo and current branch, and review the remote state. It must read the core design principles and treat them as the canonical standard. Under the investigation standard, it is required to refine context from local file paths, execution boundaries, and traces, not just memory. The requirements quality section forces the agent to produce verifiable behavior, ensuring every requirement has a stable ID and explicit acceptance criteria. Finally, the design production rules dictate that a refactor needed decision must explicitly explain why the current boundary or API shape fails, preventing unnecessary rewrites. This meticulous instruction set prevents the LLM from hallucinating workflows or skipping vital checks. It forces the solution designer to act like a disciplined staff engineer, ensuring all upstream artifacts are completely aligned. To enforce these standards, the team relies on structured markdown templates. The requirements document template requires the agent to explicitly state the goal, outline the investigation findings, perform a mandatory design health assessment, and classify the scope. It also demands clear, itemized lists for in-scope use cases, out-of-scope boundaries, and verifiable acceptance criteria. Next is the investigation notes template. Before designing a solution, the agent must document the exact current state. It records the environment context, logs its specific terminal commands, and analyzes runtime probes. The template forces the agent to list external source findings, detail the reproduction environment, and thoroughly document findings from the code, logs, and data. Importantly, it requires the agent to explicitly state any constraints, dependencies, and open unknowns or risks, ensuring no blind spots are left before the design phase. By maintaining this strict investigation log, downstream reviewers can perfectly trace how the solution designer arrived at its conclusions.
The design spec template is the master blueprint and the most critical artifact. It begins by requiring a current state read and a clear explanation of the intended change. The agent must perform a task design health assessment, explicitly answering if a refactor is needed and providing the rationale. Next, it establishes strict terminology rules, distinguishing between subsystems, modules, folders, and files. The agent must then map out the data flow spine inventory. This involves documenting the primary execution spines, showing the exact end-to-end motion from input to provider, and the return spines. For each spine, the agent writes detailed narratives and identifies the spine actors, which are the mainline nodes advancing the core request. The ownership map is crucial. The agent must state what each mainline node owns, explicitly identifying lifecycle, state, or contract transformations. Moving into capability allocation, the template forces an existing capability or subsystem reuse check. Before inventing new structures, the agent must evaluate if a current subsystem already fits the responsibility. Finally, the agent produces the final file responsibility mapping. It defines strict ownership boundaries, ensuring authority changes hands properly and internal mechanisms stay encapsulated. It maps out interface boundaries, checking if responsibilities are singular and identity shapes are explicit. This dense, highly prescriptive structure guarantees that the solution designer produces a clean, maintainable, and logically sound architecture every single time.
To ground the LLM's understanding, we provide a concrete design examples document. These are not rigid templates, but illustrative projections of how a good design spec reads. It walks through a complete CRUD request flow, showing the exact spine inventory, the primary execution spine, from front-end to controller to application service, and the return spine. It demonstrates how to map main domain subject nodes, outline off-spine concerns like auth and audit logging, and define clean interface boundary mappings. By providing these concrete examples of both good design and bad practices to avoid, the agent learns exactly what is expected of its architectural output.
Once the design is complete, the architecture reviewer steps in. Its skill instructs it to critically evaluate the design spec before implementation starts, ensuring design flaws are caught when they are still cheap to fix. It owns the review findings, the pass-fail decision, and the boundary encapsulation review. The rules mandate that it treats the requirements doc and investigation notes as supporting context, not as a substitute for independent judgment. It must review the design independently against the canonical shared design guidance and a mandatory checklist. It checks for structural weaknesses, tight coupling, and ensures that the data flow spines are logical and well encapsulated.
After the implementation engineer writes the code reviewer takes over. Its purpose is to perform the engineering source review before API or end-to-end validation begins. The code reviewer must accept the cumulative implementation package and review it against the full artifact chain. Its skill defines rigorous classification rules. A pass means the review outcome is clean. A local fix means the bounded implementation is flawed, and it routes back to the implementation engineer. However, if the code reveals a structural issue, an ambiguous requirement, or an incorrect design artifact, it classifies it as a design impact or requirement gap, routing it back to the solution designer. The review rules are explicit. Do not collapse the review into a small summary. Treat early design artifacts as context only, and verify that the implementation preserved the reviewed task design health assessment.
To execute its review, the code reviewer uses a strict review report template. It documents the round metadata and history, tracking prior unresolved findings. It performs a source file size and structure audit, specifically looking for hard limit checks on file lengths. The core of the report is the structural and design checks section. The agent must evaluate the codebase against an exhaustive checklist, verifying empty indirection, appropriate separation of concerns, and boundary encapsulation. It then fills out a mandatory 10-point scorecard, evaluating factors like data flow spine inventory, shared structure tightness, naming quality, and legacy retention. It explicitly logs its findings, provides verdicts on test quality and validation readiness, and concludes with a definitive classification. This creates a highly transparent, auditable trail of the review process, ensuring no structural compromises slip through the cracks. Let's look at a live, complex task in action, where the team is fixing a UI bug related to multimodal context files. Here, the solution designer has produced a massive, highly detailed design spec based on its investigation. In the requirements document, it clearly outlines the problem statement. User-attached files in the front end are missing absolute reference paths when reaching the back end, causing failures during validation. Looking at the investigation notes, we can see the agent deeply probed the runtime environment. It documented the current execution flow, tracing how front-end context attachments are sent via WebSockets, processed by native AutoByteus runtimes through the agent input pipeline, and eventually passed to the Claude SDK runtimes. Moving to the design spec, the agent defines the intended change. It proposes adding a small current context file reference utility and invoking it directly within the 3 runtime input constructors while avoiding broad architectural rewrites. The data flow spine inventory meticulously maps the primary execution spine from the front-end user sends through the native runtime input composition to the codecs and Claude input mappers.
In the ownership map, the agent explicitly defines that the front end owns collecting attachments, but the back-end command handlers own translating transport payloads into context file records. Furthermore, the draft file responsibility mapping explicitly calls out the target files, explaining exactly why each file owns its specific domain boundary. As we scroll through the artifacts, notice the sheer depth of the analysis. The agent logged its exact terminal commands, like git fetch, git worktree, and ripgrep searches, proving it actually navigated the file system to find the affected paths. When we reach the final file responsibility mapping, the agent is extremely specific. It assigns the context file local path resolver as the target utility, ensuring that the native, codex, and Claude adapt.
After the implementation engineer has written the code based on that exact design spec, the code reviewer generates its comprehensive review report. We can see this is round 2 of the review process. In the round history, it notes that in round 1, it found a local task surface layout issue, designated as CR001, and routed it back to the implementation engineer for a fix. Now in round 2, the review scope section confirms the changed implementation areas. Under the prior findings resolution check, it explicitly verifies that CR001, the mobile work shell surface flex issue, has been completely resolved. It verified that the view now correctly uses an overflow hidden bounded flex container, and noted the focused AutoByteus tests that now pass as a result. As we scroll through the source file size and structure audit, the code reviewer has itemized every single changed file, from the launcher foreground XML to the mobile chat view component, verifying that none exceed the 500-line hard limit. In the massive structural and design check section, the agent systematically verifies the codebase against the architectural rules. It confirms the task design health assessment is present, data flow spine inventory clarity is preserved, and ownership boundaries remain intact. Finally, we reach the review scorecard. The agent evaluates the implementation across 10 critical categories, awarding perfect scores for data flow spine inventory, separation of concerns, and validation readiness. It awards a 9.3 out of 10 overall. Notice how the code reviewer doesn't just say, "looks good to me." It provides mathematical, structural proof of correctness. It lists the exact line counts of modified files, verifies the specific CSS and Flexbox changes made to resolve the UI containment bug, and correlates those UI changes directly back to the focused layout contract assertions in the test suite. By forcing the LLM to output this highly structured review report, we extract its maximum reasoning capabilities, ensuring it checks every possible edge case, boundary violation, and regression risk before handing the ticket off for final end-to-end validation. Finally, the package is routed to the API and end-to-end engineer. This agent takes the validated implementation and runs the full suite of automated tests. We can see the terminal output as it executes the VyTest suites, ensuring that the layout containment logic, the context file path resolutions, and the API boundaries all function correctly in the runtime environment. Once all the tests pass and the validation report is generated, the ticket moves to the delivery engineer. The delivery engineer reviews the entire artifact chain, from requirements to design, review, and validation reports. It packages the final release notes, merges the branch, and cleanly closes out the workflow. This complete end-to-end process demonstrates the true power of the AutoByteus agent team, taking a complex, ambiguous problem, structurally designing a solution, meticulously reviewing the code, and autonomously delivering a production-ready fix without human intervention.
By combining specialized agents, strict skill definitions, and rigorous templates, the AutoByteus software engineering team delivers complete, high-quality code changes autonomously.